this on? Okay. Hi everyone, welcome to the last Compass Wednesday seminar of the semester. Today we're delighted to introduce one of the OCE core faculty, Milan Curcic. And okay, so Milan received his undergraduate degree in Serbia, and he studied at the University of Belgrade in 2009. And there he got his BS in meteorology and also broke into the numerical modeling field. After receiving his bachelor's, he worked as a tattoo artist for a brief period at his own shop before moving to Miami to start a PhD with Choi Chen. And the fruit of his labor was a momentum conserving atmosphere wave ocean coupled model, and he graduated with his PhD in 2015. From there, he moved on to start a couple of postdocs. So he worked at the University of Washington and then worked with Brian House in Sustain here at Erasmus for a short period until he began as an assistant scientist, also with Sustain. And in 2024, he began a core faculty position with both Erasmus and the Frost Institute for Data Science and Computing. Milan has generously spearheaded the Lunch Bites seminar, which I'll speak for everyone and say that has been a great help. And so Milan's research still handles coupled models, and he's now been focused on resolving physics of the ocean surface wave field in numerical models. So today he'll be sharing results from his recent work involving current gradients and the wave action balance equation used in global wave forecast models. So I will turn it over to you, Milan.
Thanks, Susan.
Take it away.
Thanks everyone for coming. I tend to have a Compass seminar around this time of the year because I like to go, in May I like to go to an annual wave conference called WISE. So I usually use this to kind of get internal feedback on a topic I'm working on for WISE. And this is a somewhat new topic for me, not necessarily the equation itself, but the concept of like going into wave current interactions in more detail. And this kind of started as a side quest prompted by an anonymous reviewer to a paper from last year. The paper was using this equation, but on a little bit, it wasn't considering mean currents, it was considering interactions with other waves. And that was one of the governing equations I used, and this really great reviewer pointed out, but how do you know that the equation you're using is valid in the conditions you're using it? Can you show the limits? And then I dug kind of deep in the process of revising that paper, which then brought me to this sort of limitation to this equation about how the ambient velocities need to be for the wave conservation to hold. And then I thought, but hold on, waves are being run over current fields. Whenever you run a wave prediction model and you consider ocean currents in it, there is an embedded assumption that allows the equation to hold, and that's what this seminar is about. So first I want to gently introduce you to surface wave prediction or forecasting. And this is just a global map of significant wave heights. It's from ERA 5, which I'm sure many of you have at some point used or at least heard about. It's a reanalysis product, but of course under all reanalysis products, they're based on models with some data, observational data simulated in. And you can pull out for many decades, long record of recent history, you can pull out spatial maps, not only of atmosphere, but also of wave fields, because ECMWF atmospheric model is coupled to a wave model, and they run that all together. And this is an example significant wave height map, global map, which you see mostly large values in the Southern Ocean. And this is because you have a lot of storms kind of having an uninterrupted path over in the Southern Ocean. And these storms with strong winds, they're generating very high waves, and these waves are propagating across the Indian Ocean, across the Pacific, across the South Atlantic. You get similar thing on the Northern Hemisphere from mid to high latitude cyclones. That's, for example, how we occasionally get swell here in South Florida coming from the North Atlantic. Perhaps a little more revealing about this propagation of long waves, or swell, is if we look at, rather than wave height, if we look at peak wave periods. So the color bar is in seconds. So brighter is longer period, which corresponds to longer waves. And here what you see, you can basically see wave fronts propagating ahead of these storms. So where you see these light orange to yellow bars, that's long swell propagating ahead of the storms. Now, global wave forecast models, they work really well. They're based on a relatively simple and one equation that has some terms parameterized in for wind growth and wave dissipation. But the governing equation that gives you the transport of waves is very simple. It's just a single equation, unlike, say, primitive equations for the atmosphere or the ocean, which are a system of equations where you need to together solve for both velocities and scalars. Here we're really solving for a scalar that is defined over different frequencies and over different directions. Now, I said the models work really well, but they still struggle with some things, and one part that the models still struggle a lot with is the time of arrival of swells that propagate over long distances over the ocean, exact locations on the coast where the peak of the swell will hit, and the peaks themselves. Now, it's people in the wave community know well that currents affect waves, and I'll explain in more detail how exactly. But this is from, unfortunately, the reference, which is from Fabrice Ardouin paper in 2017. It's a little cut off. But basically, it was one of the first papers to really show that wave heights on scales, say 10 to 100 kilometers, their variations are mostly governed by the variations in currents. So here in this example, you have, this is all from models. So this is the Gulf Stream, velocity magnitude. The upper left map is the significant wave height with current. The bottom left is without current. And you can see that you get a lot more structure when you include current in your wave propagation. And then they also do some sensitivity experiments by smoothing the currents and seeing how that impacts the structure of the waves. But the key point here is that if you don't consider currents, especially when we have strong currents with large current gradients, so you get that a lot in western boundary currents like Gulf Stream, then you'll miss out on the structuring waves in the wave fields in response to those currents. Okay, now what governs this exactly? Why do waves, why are they affected by currents? So the governing equation for basically all surface wave forecast models on large scales, so these models are spectral, they're not phase resolved, they're phase averaged, meaning that they model a distribution of wave energies, or more specifically wave action. So wave action is just energy divided by frequency. And you don't have to worry too much about the detail why action rather than energy. It turns out action is the one that is conserved when you have variation in currents. Energy is not. But basically you have tendency in time, that's your first term. Then you have a transport term. The transport flux has the group speed. That's wave's own propagation speed. And you have U is just the current. And on the right-hand side, now you have sources and sinks, which govern how should waves grow when you have wind blowing over, how should waves dissipate when they become too steep, and so on. Going forward in this seminar, I will completely focus on the left-hand side, and I will ignore the right-hand side because we want to really isolate this one process. Basically, what happens when we start including strong variations in U? How does that affect waves? Yeah, here I say simply a historically tremendously successful equation used daily for surf forecast, marine safety, shipping, coastal infrastructure, etc. So this is under all spectral wave models. It works well, except for some gaps that we're trying to fill in. Okay, so I wasn't sure how much to go into this, but I want to give just a little bit of a kind of origin story of where it comes from. But it's based on this concept of the variation of a Lagrangian, which to the very small limits integrated over an area must remain zero. And starting from the Bussinesq equations, and here you will probably recognize the part of the Bernoulli equation. Essentially what this Lagrangian is the difference between kinetic and potential energy of the system in a particle following frame. And then this is piped through the Euler-Lagrange equation, which then gives you, actually before I get into that, I just want to point out that this being the Lagrangian for waves is not something that is derived, but something that was taken to start with, and then it's shown that you get a conservation law from it. So unlike a lot of other fluid mechanics, for the wave action balance, there was no obvious conservation law before people started doing this. Actually, people until mid-60s did not know what is the conserved quantity for waves. It turns out it's this so-called wave action. And the approach is based on phase averaging too. And this phase averaging introduces restrictions on how much are things allowed to vary within a single phase of a wave. So they have to vary very little, so that to a leading order you can basically put them out of this integral where you do the phase averaging. So by combining the Bernoulli equation as the Lagrangian and then putting all the terms and working out the integral, you get that the average Lagrangian is this. Now 1/2 GA squared is the total wave energy, so you may recognize that. Omega squared over GK, you will notice that resembles the dispersion relation for gravity waves. So L equaling 0 is actually the dispersion relation, because for it to be 0, this needs to be 1. And this is 1 for exactly the dispersion relation of gravity waves. Then when you take that through the Euler-Lagrange equation, you get this. And it was Bretherton Garrett 1968 was the first paper to show that you can do this with mean and slowly varying currents as well. So there are some extra terms here on the right-hand side that you don't normally see in wave models. because in this paper they just said, but within the limits of small epsilon, this actually also drops out, so it can be neglected. So this, off the bat, this comes out of the integral, and then off the bat they say this will always be smaller than this. So then, as epsilon tends to 0, you're only left with these terms, and that's what went into all the spectral wave models. So when you read spectral wave modeling papers, they'll kind of start from this, and they say currents must be slowly varying in time and space. That's what this means, small epsilon. So this is the variation in time relative to the wave scale. This is the variation of current in space relative to the wave scale. So they're all assumed to approach 0. Now, this kind of logic started going back 50 years ago, but then over the course of last 20 years, as satellites are getting better and as people put more drifters into the ocean, all kinds of field campaigns to measure the submesoscales, people find that the more you zoom in onto the ocean, the more structures you find. It's not like you zoom in and you get a constant field because you zoomed in. It's almost like the pixels, as you blow them up, they impact themselves into more pixels. So then it's worth revisiting, well, if we resolve more and more, and if we resolve a very active, full of high gradient submesoscale current field, what does that do to this? Is the equation still valid? And whether maybe these terms should be included and within what limit. So I just want to point out again that this still needs to be, for this equation to work out from the previous slide, this needs to be relatively small. But that doesn't mean that these terms are necessarily 0. Actually, I would argue that even if this is small, you're still more accurate if you keep these terms, even if they're a small contribution, than dropping them. And 50 years ago, it made sense to drop as many terms as you could for simplicity. Okay, so this is the same thing, but simplified. I have unpacked these terms into individual terms so that I can explain them to you. I have also dropped the time-dependent part, because it turns out with the data that we have, the time-dependent part is much smaller than the spatially varying part. So I keep the spatially varying part. And I also changed the notation. So there's a little nuance about what is this big U and what is little u prime. And this is just a scale decomposition. Suppose that you have a wave model over a 10 kilometer grid with a 10 kilometer resolution. So your grid cell is 10 kilometers. And suppose that within the 10 kilometer grid cell, you are resolving fine current structures. Now, maybe you don't have measurements of that fine structure, but let's say you have a very high resolution ocean model. So in that case, this big U going forward represents the mean current in the grid cell. And the little u, specifically the gradient, is just the gradient within that grid cell. So say if this is my grid cell and I have currents that's doing something like this, if I take the average, that's by u, but if I take the first derivative of this, I'm calling that del u del x. So I'm not necessarily concerned with these small wiggles, because with the equation at this first order we cannot resolve the wiggles, but we can resolve this one gradient within the grid cell. Okay, so now let's explain these terms. Oh, I realized I kept this one. I shouldn't have kept that one. So ignore this one. But I said already this is a tendency. Now, Cg is the group speed times the gradient of del n over del x. That's just the propagation. Now, in this frame, we're not going to consider changes in Cg. So this is literally just a solid body advection by a constant velocity. Okay. Then you have the same thing, but advection by the mean current. Then you have the strain, or the convergence in the currents causing the change in n. So if you have a lot of n in a space where you have large current convergence or divergence, that's going to cause it to grow or decrease. I'm skipping this one, so we drop this. And then this guy is also strain due to current convergence or divergence, but not within the grid cell. So this is subgrid scale current that we're not normally resolving, but suppose that you have very high resolution either ocean measurements, say from a satellite or from a model. This would be the contribution of that. And then we ask, what is the effect of unresolved currents on wave propagation? So I'll be looking at not only this, but I'll also be looking at this guy here, because as we change our resolution of the ocean currents, its contribution will change too. Okay, and to do that, I need really, really, really high resolution ocean. This is a simulation from Roy Barkan, at the time from UCLA. So it's ROMs, it's nested down to this area in the Gulf. So this is 150 meters resolution. This box, I don't recall the outer boxes, but I think it scales out. This whole parent domain is perhaps 3 kilometer resolution. So still fairly high resolution, but I'm really interested in the highest resolution available. And this is what surface velocity looks like from that box. So this is 150 meter resolution. So you see a lot of, it looks, you can see more detail on my screen actually than here, but like there's a lot of like fine scale details if you look. The more you zoom in, the more features you see. Here going northwest to southeast is a submesoscale front, so you can see that in the U and V components. So you have, so red is positive, so you have flow going toward the right, blue is toward the left, so you have convergence. Here you have divergence in the V component. So basically flow is basically going from upper left or lower right on this side and the opposite way on the other side of the front. And I want to look at what happens to the waves as they propagate across this. Now you can play all kinds of games, but I started with south to north propagation. And I want to see how the wave packet will respond to all these. Now, to test the sensitivity, I want to see what do waves do if I force them with currents of different scales. So I artificially coarsen the model going from 150 to 360, 600, 1200, 2400, 4800. So I double the coarsening each time. And basically what you see that as you do this to the, you do this to the velocity field, and then you look at the magnitude. As you go coarser and coarser, you lose the detail. You still maintain the magnitude of the large scale stuff, so that's expected. But recall that for waves, gradients really matter. And when you coarsen the fields and then you look at the magnitude of the gradient, you lose not only the structure, but you also lose the magnitude. That's also expected. So you have a lot more fine scale and high magnitude gradients here all the way on the left. So that's the native resolution. Then as you go toward the right, it disappears. Now this is almost the same thing as the previous one, except I scaled down, I normalized the gradients with the magnitude of the velocity, and I do that because this value is actually k epsilon, and epsilon is my asymptotic limit parameter. So if I pick for the waves, if I pick a wave number of 1, so that's about a 6 meter long wave, then this epsilon gets to 0.01. So we're still mostly okay. That's like 1% of the whole thing. But if I picked, for example, k of 0.1, then I'd be approaching that asymptotic limit where the wave action maybe doesn't work as well. And that's because as I decrease wave number and my wave gets longer, now the current can vary much more within that wavelength than for shorter waves. So the scale of waves also matters. So going forward, I stick to k of 1 because that's what I know for sure does not break any equations. And then in a near future work, I plan to explore the limits of wave scales and the current gradients and the limits of epsilon. Okay, and I do all this with numerical experiments. So basically I'm going to take, in the middle of the domain longitudinally, I'm going to take a meridional transect, and I'm going to propagate waves from south to north across this front. I'm going to do it every 6 hours. I have 1 month worth of this high resolution simulation, so I don't want to bias my results by choosing a specific time. So I run every 6 hours, and I run it for 24 hours. 24 hours is basically your k of 1 wave number wave gets from about here to about here. So I don't want them to leave the domain, I want them to stay within the domain, but I want to have as long as I can to get the effects. So every 6 hours gives me 121 ensemble members, and then I'm running them with each resolution of my coarse and current fields. And then I want to quantify the contributions of each terms to the solution. And my experiments are in increasing levels of complexity. So I first run with no currents, only wave propagation. I just want to show you that we get what we expect. That's not particularly interesting. Then I add grid-resolved currents. So all wave models already do this if they have the current fields. And then experiment 3 has this term of subgrid unresolved currents that wave models currently don't do anything about. Okay, so this is the boring experiment with no currents. Blue is my initial, I just initialize a Gaussian field of wave action with a peak of 1, and I let it propagate with a constant CG because CG is constant. This just moves without changing form. So we expect that. That's the solid body attraction. And each thin line here is a 1 hour increment. So basically it tells you how this envelope moves from left to right. The second panel is the same view, just shown in a time on the y-axis, and the color indicates the density of the field. So this corresponds exactly to this, just time dimension is added on the y-axis. Now in experiment 2, I'm adding currents, grid resolved, at 150 meter resolution, and now you get deformation of the field. You also get somewhat of a lag in arrival. So normally it should arrive with a peak at about 175, but because we start with the southward currents, and there's more southward currents than northward currents, that ends up slowing down the packet. It even steepens it due to convergences. So we arrive with a somewhat stretched out and slowed down field. So we have a decrease in the peak, we have a more diffused, kind of more distributed field, and we have field that has slowed down. And you can see that slowing down here too. So this has a smaller angle of propagating in time than this. So basically there's slowdown here and then going. That's because, so here, what you see in blue here is the current against the waves. So that's slowing down the waves. And then when waves propagate over this field of northward current, then they go a little faster. And they end up here. And then I repeat this for each resolution. I will gradually coarsen it. I won't go into details, but I want you to watch that as I coarsen the resolution, I'm starting to lose detail in the perturbations to the wave packet. Basically, everything ends up being smoother. We still get some smoothing out, so we still have the gradients in the velocity, southward and northward. So that causes this slowing down and stretching, but we lose the very fine scale structure as the packet propagates. Okay, experiment 3. Now I'm adding the subgrid scale strain. Unfortunately, I didn't do this right, so the bottom panel is off the screen, but it has a lot of fine scale structure. Its magnitude is smaller than this, but you won't recall what the previous one looked like, but basically you end up getting more cragginess in the wave field due to these very subgrid scale convergences, divergences, and you end up with somewhat more irregular structure in the end.
Quick question.
Mm-hmm.
The third panel, is it current magnitude or is it one of the two components?
So it's the current magnitude, but because I'm in 1D, it only sees negative and positive. Yeah. So blue will be against the waves and red is with the waves. And the same thing happens as I decrease the resolution and coarsen the current fields. We lose this structure as we go. Okay, now in a little more quantitative way, I want to show you the effects of grid resolved and subgrid scale currents on the wave packet. And I'm only be showing you initial. Final without currents is just for reference. That's where the packet would arrive if there were no currents. And the green is the final with currents, so it's delayed, it's decreased, and it's a little bit stretched out. And this is at 150 meters. Now at 300 meters, I can also have subgrid scale resolved strain. So that strain comes from me coarsening, so averaging over the 4 grid cells, and then calculating the subgrid gradient within that. So now with this subgrid current strain, you actually get a little bit even more decrease in the peak. Now this is, I'm showing you a very specific case initialized on that hour 600 of the simulation. So it's somewhere in the middle or toward the end. So it's just an example. It's not representative of the whole ensemble, but I'll get to summary results very soon. Yeah, so now this is a 300, this is a 600, 1200. So as I coarsen, the bump goes down, and it's almost like I get a little bit more contribution from the strain at lower resolutions than I did at high resolutions. But overall, you can eyeball this to be about maybe 10 or 15% decrease in the orange relative to the green. Okay, so then I summarize all these results, basically all the 121 ensembles, to try to remove bias from picking any specific time. Now there will still be bias related to this specific simulation. So this is 1 winter month, just outside of Mississippi River outflow in the Northern Gulf. So it's intentionally placed there to look at submesoscale activity due to that outflow. And for me, it was a very good case to use because I knew that I would find a lot of submesoscale activity because I really wanted to kind of push this to the edge. Of course, not all of the global ocean is as active as that is, but because of that choice of a winter month that is a little more active than summer month, for example, take these summer results as specific to that case and are not necessarily representative of like the whole globe whenever. But what I found based on 24-hour propagation of a wave train over submesoscale front, the grid resolved current reduced the swell peak by 20 to 45% on average. So the highest resolution you get a 20% effect. And then as you increase resolution, as you coarsen, that effect is greater. This is because by coarsening, you're excluding more and more of fine scale current activity. And so you're basically excluding that effect by not representing the data. So subgrid-scale strain, regardless of resolution, is still relatively small. Maybe you can say that the effect increases as we coarsen, but it is about 10% of the grid resolved effect, so maybe about 5% overall. And then I also find, okay, this is the detail I omitted. All the terms except for the subgrid ones are adiabatic, they're conservative for the action. But I introduced a term that is basically either taking action out of the ocean or putting it back into the ocean. So if you were coupling this with the ocean model, for example, if you want it to be conservative, say if waves are getting energy from the subgrid strain, you would need to take that energy out of your circulation. I'm not saying how exactly, but if you want to conserve it, you need to do it, because that term is the only one that is essentially acting as a source or sink term for the action. But overall, regardless of resolution, including that term, basically, at least in this case, it decreases the total action by about 15% on average, but with a fairly large spread. There's actually orange shading here. And there are some individual ensemble members that actually go positive, meaning that the wave field actually got energy from the currents. So that would happen if you had more convergences than divergences. If you had equal amount of convergence and divergences, you won't have a change. But this just means that in this current field at this time, there was more wave energy loss, essentially, to the ocean rather than gain from convergences. Okay. My takeaways are wave propagation is sensitive to strong current gradients, so I find between 20 to 45% effect on the maximum. So this is over a 1-day propagation over an intense submesoscale field. This means approximately, because action scales with energy and energy scales with amplitude squared, that means that, say, for a 20% change in energy, you would get a larger change. I can't work out the math exactly in my head, but you would get an even larger change in the observed wave height. Now, what you see mostly is that the packet got spread out, which means that you would be getting waves, say you're at the beach, and this wave packet propagates toward you. Because of that spreading out, you would get waves to be more diffuse over time, so maybe you would see them for a longer time, but at a lower, with a lower peak. For most of these, and for not too long of waves, the governing equation is still valid within the original asymptotic limit. And the subgrid-scale string term, I believe, should be considered for inclusion in models when high-resolution currents are available. Now, an unspoken or unwritten question here, but I'm going to speak about it, is like, when does this matter? Like, when do we really have high-resolution enough currents to include in coarser resolution wave models? Well, I think most immediately this is probably relevant in coupled wave ocean systems. So if you have high resolution ocean and you have waves, say, at a coarser resolution, and that's a common scenario because wave models tend to be quite computationally expensive. For example, the global ones run by NOAA or ECMWF are quarter degree resolution. Within a quarter degree, a lot can happen with ocean circulation currents. But there are also satellite platforms, emerging satellite platforms that are resolving both currents and waves at increasingly finer resolution. Now people even see individual wave groups from a satellite. That's very exciting. But this is something that's perhaps most readily apparent from this theoretical and numerical point of view. In practice, I think the technology is not quite there yet for this to be immediately applicable. Ultimately, you run into this limit of, well, I don't have high resolution currents than this. And here I was asking, what if you did? What does that to waves? So what this actually tells you more is, with current wave models, it kind of gives you an estimate of the error that you have by not having high resolution currents. So maybe if anything, this is more an argument of having more and higher quality and high resolution current measurements from satellites. Okay, I think I can stop here. Timing is good, and I'll take questions. Thank you.
Thank you, Milan. Do we have any questions?
Yeah. Thank you for an interesting talk. There are some places where there is high-resolution current data. Nick Shea's work in the Straits of Florida has some fairly high-resolution current data, and there's also probably some high-resolution wave data to go with it. And the Gulf Stream as a whole is rather convergent at the surface, and when you get north winds, you tend to focus the energy, and so you'd have both that amplification effect and the convergence going for you. And if you have the resolution that Shea has, it would make a difference. I have friends who are sailors who were capsized outside of an eddy by the focusing of waves through that eddy like a lens, and tossed a 45-foot trimaran over very unceremoniously. So these small scale things do make a big difference if you happen to be at the right place at the wrong time.
Indeed, yeah, and there's even, I can get cite anything specific on top of my head, but there's even a work on trying to link wave current interactions and focusing with rogue wave appearance. Brian had a question.
Thank you.
Thank you.
Well, it's kind of interesting, almost the same, related to John's question, but it was about if you have high enough shear, like in the north wall of the Gulf Stream, wouldn't it still be an important process whether you have a really high resolution current model? And I think anybody that looks at that there, the north wall, for example, the shear is very high, right? The model resolution does smear it out quite a bit when you look at that, but you when you look at actual measurements at that point. But Mike was a great talk, really interested because, I always looked at the shear in the current field as affecting the short waves more because it was left because of the simplification of the equation and the relative group velocity. Now you have pointed out that it's still affecting the long waves. We just haven't included it in the equation, which I think is a really interesting result. Do you have any kind of idea where that boundary would be?
Yeah. Yeah, so the overall effect is probably larger. Just magnitude, if you look at characteristic group speeds, for example, for the wave that I used here, group speed is 1.5 meters per second. So that's actually with, the western boundary current magnitudes, it's quite possible to get full blocking of that kind of wave if you have a 1.5 meter per second current countering the wave. So because short waves travel more slowly, that effect is proportionally greater on the short waves. Shorter waves, also because of their travel speed, spend longer time traveling through an area of higher convergence or divergence, so they get affected more. Longer waves, because they move faster, they kind of sweep through. But yeah, they still, I did very briefly look at effects on longer waves, say K of 0.1, so that would be a 60 meter long wave. And yeah, absolutely, the effects are smaller on this scale, but I bet that they would still be significant on a, say, across Pacific scale. And a lot of big swell travels from Southern Ocean across the Pacific, I mean, even to the west coast of North America. I kind of rambled on. Did I answer anything specifically?
Yeah, I mean, it's an interesting.
Okay. Thank you very much. My turn to ramble about it. So I would think that when you coarsen the velocity field, you basically average out, and I would think that the subgrid-scale strain term that you add back, right, would be a way of palliating for that coarsening. However, I'm seeing in your result, in your one example, that it doesn't do much. Is that the right interpretation of the results?
You know what? Let me look at first at this summary one. So the top one is the maximum. So that's the maximum of the peak packet. The second one is the change in location of arrival. So that one, actually mean currents matter for that one, but the current gradients don't do much to it. That's also physically reasonable and explainable. And then the bottom one is the total change of. So maybe the most relevant one to look at is this top one. So again, this is the average over 121 ensemble members, depending on the time.
So do you think that result is like specific to your example, or do you think or do you have a feeling that it's a general finding?
So what I'm looking for here is the ballpark relative change, and that seemed to be, let's say, about 0.2 or 0.3. Now, the fact that it's negative rather than positive, that's a case specific, so region and time specific, because there are some ensemble members at specific times. If you send the wave right at the right time, you will actually get an increase in the peak at arrival.
What is the third panel in that slide?
So the third panel, so it's just a sum of the total action, which you can think of as total wave energy in the system. So
that shows a lot of changes?
Yeah, so the green one, because the green doesn't have any non-conservative terms, that always stays zero, like the change is zero. But the only one that has a change, and it's about 15% on average, is this subgrid strain term. That's the term that is essentially a source or a sink. And in this case, it seems to be a sink. And I think that's specific to just this current field. I think if we had a equivalent simulation somewhere else at a different time, it could be different. And
Uh-oh.
see if it comes back. Okay. Can't show you that slide now. I could offline. What I want to show and point out is that during the travel of the packet, there's a region of the ocean where a lot of stuff gets amplified and then it gets dampened again later. It's almost like it goes through a thing where it gets excited and then it kind of gets diffused later on. So and I believe that had to do exactly over the placement of the front. That's where the strongest gradient is. Thanks, Shen.
Anyone else?
I saw Ming and I saw Dale.
Milan, can you comment on the direction spreading for your simulation? The wave direction?
No, I cannot because I didn't do that. I did 1D intentionally to start because doing things 2D with directional spreading adds multiple complications. So one is you have twice as many terms because now you have terms in the cross direction. Another one is basically numerical diffusion in the lateral sense. So I started with 1D. I do plan to do 2D, hopefully before the conference next month, and maybe I'll have an answer for you. But what's the specific question? Maybe I can see what I expect to get.
Yeah, because I was seeing some literature saying in this submesoscale regime that the direction spreading is more important because based on your simulation, it seems that it's like a frequency shifting, right, from high frequency to low frequency in this case, right?
I don't have any change in frequency, so there is that. So there would be a compression of the wave number due to currents. I'm not modeling that. I'm only modeling action density of a single wave number. So that's even more simplified. I don't know if we can say directional spreading is more important than something else. Directional spreading is just what happens, like waves spread directionally. But it is, I think it is more difficult to model proper directional spreading. It's just when things are set up on X and Y axis, things don't like to propagate in between the axes. They like to go along X and along Y, but if you go in between, a lot of lower order numerical differencing schemes, they over diffuse laterally.
Okay, thanks.
But that's a whole another big topic.
Thank you. I'm just curious, when you try to coarsen your current field, do you have any upper bound before your equation or the hold in the system?
Can you repeat that?
When you try coarsen your surface current field, do you have the largest grid possible before your wave action equation no longer hold, or it's just fine to keep coarsen the current field?
Okay. No, you can coarsen as much as you want. Global wave models typically run at a quarter degree, so that's 20-something kilometers, and then you run half degree resolution. So they work well on you can coarsen as much as you like. It's more problematic if you refine, because you run into theoretical limitations of the fact that you could be modeling the action density of a 300-meter long wave, but on a 100-meter grid cell. And that probably breaks something about the assumptions of the phase averaging in the action balance derivation. That's also why I stayed with a relatively short wave, so K of 1, because I knew that even at 150-meter resolution, I'm not violating it.
Thank you.
Anyone
Thank
else? Okay, I have a question. Do you think that the reduction in the significant wave height for some fraction of the waves could influence air-sea coupling, maybe with airflow separation or another type of flux term?
Yeah. I mean, it will influence waves. Let me find a good experiment. Okay, this is experiment 3 at the highest resolution. So this is what I wanted to point out. So this is about where we it's hard to tell. Maybe this is we are 1/3 or maybe close to 1/2 of the simulation there. So this probably happens when we pass this spot. So this seems to be a high grade. Basically, you have strong countercurrent, then you have this. So one thing that I don't do anything about here is that these waves could be becoming steep enough to break. So they could be triggering additional wave dissipation. But I'm completely conservative in how I simulate this. So I just propagate the packet. But yeah, I mean, you could have enhanced wave dissipation. So when waves grow, they also steepen. So I keep k equals 1 constant here, but action increases, so the amplitude increases, so the steepness increases. So they could become steep enough to break. They could become steep enough to affect the airflow, and then affect the wind stress. And I think I've seen some papers about specifically looking at wind stress modulation by submesoscale fronts. I think Ming did something like that. Maybe Ming did exactly that for his PhD. I apologize, Ming.
I have that paper title in my mind as you were speaking, because I was thinking about mesoscale, like eddies, and this seems like it could be pretty exciting to run over the Agulhas current region, perhaps to see what.
So supposedly Agulhas region gets a lot of freak waves too. And by the way, here in the bear cut, you can often see during high tide, because there's I think it's a sandbar underneath where the flow accelerates over. And then when you have some local wind-driven wave coming from the other side, you can watch the blocking right there.
Well, thank you, Milan.
Thank you.